In this lesson, we are going to review some properties of exponential expressions. And an exponential expression is an expression of the form a to the x, where a is called the base of the exponential expression and x is called the exponent. And I'm going to go through some basic properties. And on this slide, I have a list of those properties, and through the remaining slides, I will go through more details on each one. Starting with the zero exponent rule, which says that a number raised to the zeroth exponent is equal to 1. So if you take any number raised to the zeroth power, you end up with 1, provided that the base is not actually 0, because as you learn in calculus, 0 to the zeroth power is called an indeterminate form. But you don't have to worry about that here. Next is the identity rule, which says that any number raised to the first power is itself. Then we have the rule for evaluating an integer exponent. So if we have some base raised to an integer exponent, such as 4 for instance, that means we need to take that base and multiply it 4 times, or whatever n happens to be. We have the product rule, which says that a number raised to a base raised to an exponent times that same base raised to possibly a different exponent, or it could be the same, is equal to that same base raised to the x plus y. You add those exponents together. So when you multiply exponential expressions, you end up adding their exponents. Then the exponent rule. So if you have an exponential expression raised to a power, you multiply those exponents. You can simplify, but you have to multiply. The product to a power rule says that if you have a product of bases inside parentheses, which are raised to an exponent, then you raise each one of the bases inside the parentheses to that exponent. Then we have the quotient rule, which says that if you have two bases that are the same, raised to exponents, could be different, could be the same, and those are divided, then you subtract their exponents. Then the quotient to a power rule says that if you have a fraction raised to an exponent, then to evaluate that, you take the numerator and denominator separately to the same power. The negative exponent rule. A number raised to a negative exponent is the same thing as 1 over that value raised to the positive exponent. So essentially you're just moving it into the denominator, or you can see this rule as 1 over a to the negative x brings the negative a to the negative x up into the numerator as a to the x power. And lastly, the rational exponent rule, which says that a to the n over d, and I've chosen n and d to stand for numerator and denominator of that fraction, can be evaluated in one of two ways, which are completely equivalent. You have the dth root of a to the nth power, or you can take the root based off the denominator and then raise that whole thing to the same power. Alright, now let's look at these rules in detail. Alright, so zero exponents are very simple. So if you have an integer raised to the zeroth exponent, that's equal to 1. 2 to the zeroth power is 1. Or if you have, say for instance, a fraction raised to the zeroth exponent, that's equal to 1. No problem. Even if it's, some sort of irrational number, like 4 pi, for instance. You raise that to the zeroth power, the result is 1. The tricky part is when negatives are involved. So let's say, for instance, we have negative 5 to the 0th power versus negative 5 to the 0th power without parentheses. So when I include the parentheses on the negative 5, so in the first part, everything's raised to the 0th power. The result is 1. But in the second example, the 0 is only raising the 5 there to the 0th power. And in that situation, I actually end up with negative 1. So it's a little bit tricky there. But just watch out for that. But in general, anything you raise to the 0th power is just 1, except for 0 to the 0th power. As I said, you don't need to worry about it at this point in your mathematical career, but that is equal to, that is an indeterminate form. Next up is the identity rule, and that just says anything, raised to the first power is itself. 5 to the first power is 5. Negative 14 to the first power is negative 14, and that really doesn't matter if you're dealing with parentheses or non-parentheses, because this right here still evaluates to negative 14 because anything to the first power is itself and there's still a negative out front. So very straightforward. The integer exponent. So here's what happens if you have, say, like 2 to the 4th power, for instance. It tells you to take 2 multiplied 4 times. So 2 times 2 times 2 times 2 times 2 would result in 16. All right, pretty straightforward. It works for integer bases, non-integer bases, positive, negative bases. You just have to be careful with positives and negatives. So like for instance, if you have negative 2 to the 4th power versus negative 2 to the 4th power, it makes a difference. Because when you do negative 2 in parentheses to the 4th power, you're literally multiplying the value negative 2 4 different times. So there's 4 negatives, which is an even number of negative, which cancels out. That even number of negatives cancels out to a positive, and the result is positive 16. But in this situation, in 3, there's only 1 negative, because the only thing you are multiplying to the 4th power, is the 2, so it's going to be 2 to the 4th, which is 16, and then there's a negative out front. So you just have to be careful with that sort of thing. The product rule. All right, so the product rule is stating that, for example, if I have 3 to the 4th power times 3 to the 5th power, it's telling me that that should be 3 to the 9th power. But let's find out why. So it's pretty straightforward to see. If you write out what 3 to the 4th power means, and you write out what 3 to the 5th power means, well, now I just have 9 factors of 3, which can be simplified as an exponent. So essentially, when you're multiplying exponential expressions, as long as they're the same base, you can add their exponents together. The exponent rule. So let's say, for example, I have 3 to the 2nd power raised to the 3rd power. So according to the exponent rule, this should be 3 to the 6th power. And if you wanted to know what 3 to the 6th was, you could plug it into your calculator and get that result. I'm actually just only wanting to show you how these results work. So when I raise something to the 3rd power, so I'm going to look at the 3 here first. When I raise something to the 3rd power, it means to multiply that thing 3 different times. So it tells me to take 3 squared 3 times. And if I multiply out 3 groups of 3 squared, essentially that means, to do 3 times 3 times 3 times 3 times 3 times 3. So I have 3 groups of 2 factors of 3, which is essentially asking me to multiply these things together. So I have 6 factors of 3 in the end. So 3 to the 6th power is the result. So that's why it works the way it does. The product to a power rule. So if I have, for instance, let's say I have 2x to the 3rd power. So I have a product, 2x, and I'm raising that to the 3rd power. Essentially what this rule tells me is that I would take 2x times 2x times 2x, which would basically be 3 factors of 2, which would be 2 to the 3rd power, 3 factors of 3, which would be x to the 3rd power. So in effect, you basically distribute the 3 into each of the factors. And if you wanted to write the final result, in this particular case, it would be 8x to the 3rd. So that's what's happening in the product to a power rule. In the quotient rule, let's say we have 5 to the 8th power over 5 to the 3rd power. So this would mean, according to the quotient rule, that I would subtract these exponents. But why? Well, the reason is, if I write out what 5 to the 8th means, let's see, that's 1, 2, 3, 4, 5, 6, 7, 8, great, divided by 5 to the 3rd. Oops. So I end up with a lot of shared factors in the numerator and the denominator. In particular, factors of 5. There's 1 factor that cancels. There's 2 factors that cancel. There's 3 factors that cancel. And each time one of those factors cancel, the exponents in the numerator and denominator reduce by 1. So after the first group reduces, I basically end up with 7 factors of 5 in the numerator, 2 factors in the denominator. Then the next group cancels, and I have 6 in the numerator and 1 in the denominator. To eventually, I get to the point where I have 5 factors in the numerator, none in the denominator, which is essentially 5 to the 5th power. Because actually, let me show it this way. If I cancel out all the factors in the denominator, I would have 5 factors in the numerator, none in the denominator, but what is 5 to the 0th? We learned in just a second ago that is 1. So this becomes 5 to the 5th power. Now, what's interesting about the quotient rule is that, what happens when you have more factors in the denominator than in the numerator. And we'll take a look at that when we get down to negative exponents. But the whole idea behind negative exponents comes from the quotient rule. Quotient to a power rule. This is helpful thing here. Like if you have 2/3 raised to the 2nd power, then anytime you're dealing with fractions, generally things get more difficult. But when you're working with powers of fractions, it's actually pretty straightforward, because all you have to do is just take the numerator and denominator separately to that power. So in this case, 4/9. Very straightforward. It also tells us how to work with, like if we're doing the square root of a fraction, but that's really coupled with the rational exponents as well. So I'll hold off on showing you how that works. But the negative exponent rule, let's take a look at it. So back to examples with the quotient rule. Let's say I have 3 squared over 3 to the 6th power. Now, if I work this out using the quotient rule, essentially I would have 3 to the 2 minus 6, which is 3 to the negative 4. And that's a perfectly valid answer, although we generally don't write our final answer in terms of a negative exponent, because we can simplify it further. And the reason we can simplify it is this. If I look at the details of this, 3 squared over 3 to the 6th. 3 squared is 3 times 3. 3 to the 6th is 6 factors of 3. And I did 7. Sorry about that. There we go. So now, when I cancel out one factor of 3 that exists in the numerator and denominator, I essentially have, say, like 3 over 3 to the 5th. When I cancel out another one, it's like I have 3 to the 0 over 3 to the 4th, which is kind of where that 3 to the negative 4th is coming from. But if we don't evaluate 0 minus 4, then we could write this as 1 over 3 to the 4th power. And so we have two different results for the same problem. Well, what happens is negative exponents are defined as 1 over the same exponential expression, but to a positive exponent. So 3 to the negative 4th power is the exact same thing as 1 over 3 to the 4th power. And this is where it comes from, this quotient rule. The rational exponent rule. Okay, so this here basically says that if you are doing, let's say, 9 to the 3/2 power. This is a common place where you see this used. Alright, so the 3/2 power is very intimidating because, you know, it's difficult enough sometimes, especially without a calculator, to evaluate, you know, something to an exponent, because the numbers can get large. Here, this not only involves exponents, but it involves roots as well. So it can be rather difficult. But the rational exponent rule says that we can evaluate this in one of two ways. It could be the square root of 9 cubed, or it could be the square root of 9 altogether cubed. Both of these will result in the exact same answer. It makes no difference which way we go, and I'll show you in a second as to why it doesn't make a difference. But evaluating, for me, my preference is the second, because I don't really need to grab a calculator to do the second one. So for instance, the square root of 9 is 3. So I'm just going to replace the square root of 9 with 3, then 3 to the 3rd power is 27. And I'm finished. If I'm going to do it the other way, then I need to know what 9 to the 3rd power is, which I know 9 squared is 81, so 9 to the 3rd should be 243. Grab a calculator and check me if you don't mind. But regardless, then I would need to know what the square root of that answer is. So, you know, the numbers get very large that way. So I have a choice, and I can do it either way. So, why do I have a choice? Well, it comes down to just playing with rules of exponents. So, for instance, if I have 9 to the 3/2 power, I can think of it as 9 to the 3rd to the 1/2, or I can think of it as 9 to the 1/2 raised to the 3rd. And the reason that works is because when I have an exponent raised to another exponent, those simplify by multiplication. So in the first case, 3 times 1/2 is 3/2, and 1/2 times 3 is also 3/2. So they result in the same answer either way. It's just most of the time when you have no calculator available, doing the root first actually makes things a little bit easier. But rest assured, most of the time when you're using this rule in this class, you're going to be using it either just as, like for instance, let me come down a little bit, as say 9 to the 1/2 power, writing that as opposed to just square root of 9, which of course would be 3. Or if you have like 8 to the 1/3 power, that would be, the same thing as the cube root of 8, which of course would be 2. So in this class, if you're using rational exponents, you're generally going to be using them as a replacement for roots. That's all. And to show you something on your calculator here, there is ways in the calculator of doing square roots. So if you do second and x squared, square root of 9 is 3. There are ways of doing cube roots, but you have to go into the math menu and scroll down, and option 4 there on my calculator is the cube root, and then option 5 you have x root, which means you could do 4th roots, 5th roots, and so forth, whatever you wanted. If you forgot about those locating, however, and let's say you wanted to do the cube root of 8, well, you can raise 8 to the 1/3 power. That means the same thing as the cube root, and it'll calculate as 2. So nice feature of the calculator there. You can actually use rational exponents purposefully there. Just to check myself earlier, what did I say? 9 to the 3rd power was 243. Oh, I was off by a factor. 729. And then when we take the square root of 729, it should be the 27. Okay. Yeah, good thing I checked myself. Or you're, have checked me as well. That's just good. So let's move forward then and just kind of take a look at a couple of examples of how these exponential properties are probably going to be used in this class. So you're not really going to see a lot of problems in this class that ask you to just do an exponential property and that's it. You're going to use it in part of some other problem. And for instance, solving exponential equations is a lot of the times where that's going to be used. So simplifying an expression like this, for instance, would be something you would want to be able to do. So let's say, for instance, if I notice that I have the same base between 3 to the x minus 4 times 3 to the 2x, then I could simplify this by combining into a single exponential function where all I've done is just added the bases together. Since these two are being multiplied, I added my exponents together. So like terms, simplify, I could do that and get 3 to the 3x minus 4. Okay. Here's another example that you might run into in this class. Rewriting an exponential expression in terms of a different base. So for instance, I could write this as 27 to the x minus 1, but I could probably simplify it knowing that 27 is 3 to the 3rd power. And since 27 is 3 to the 3rd power, I can simplify this because I have 3 to the 3rd raised to the x minus 1. So I would multiply 3 times x minus 1, and I could say this is 3 to the 3x minus 3. So there's going to be times where there's going to be an advantage in doing that, in expressing an exponential expression in terms of a different base. All right, next up, solving equations. You've probably seen situations where you've used something like this before, but I think it's useful to really explain in terms of the rational exponents. So for instance here, what you want to do is you want to get x by itself. And since x is being cubed, then most people know the next step is to take the cube root of both sides. And that makes sense because if you cube something, the inverse of that is the cube root. So the cube and the cube root cancel, and you result with an answer of 2. But another way of looking at this is if I have x to the third equals 8. I could use rational exponents and say this is x to the third to the 1/3 equals 8 to the 1/3. And 3 times 1/3, when I simplify that, is 1, so I get x to the first power, which means I have x by itself. 8 to the 1/3 power means to take the cube root of 8, so I get 2. So I still result in the same answer of x equals 2. And there's just a different way of looking at that. Similarly, oops, went too far, there we go. This next example basically just does the opposite. And I'm just using cube roots and cubes over and over again just because the numbers are small. You use larger roots and it just gets to be bloated numbers. So when you're taking the cube root of this item, the inverse of that is a cube. And the reason that I know that is because I could rewrite this as x plus 2 to the 1/3 power. And what I'm trying to do is get rid of that 1/3 power. So in my next step, I have x plus 2 to the first, which I'll just leave that first power off, equals something. And we'll figure out what that something is in just a second. But where it comes from is taking both sides of this equation and raising it to the third power. And how do I know that I'm raising it to the third power instead of raising it to the 1/3? So I know I'm raising it to the third because 3 times 1/3 result in an exponent of 1, which means I get that exponent. I get the x plus 2 by itself. So then this is equal to 8. And then when I subtract 2 from both sides, I get a result of x equals 6. So when I see problems like this, I see that students will often make mistakes and try and take the cube root of both sides in this situation. Which if you did that, you would essentially have x plus 2 to the 1/9 power equals the cube root of 2. And the cube root of 2 is even a non-integer value, so the problem's getting a good bit more complex at that point. So that should get you started on the types of exponential expression properties that you need for this class.